So in this video I'm going to discuss the question in thermal and statistical mechanics which appeared in GATE 2018 examination. So let's take a look at the first problem. The statement is, at low temperature T, the specific heat of common metal is described by with alpha and beta as constant. Okay, so at low temperature the specific heat contribution, is given as C, that is equal to alpha T plus beta T cube. So the linear term in the temperature that arises from the electronic contribution to the specific heat. This is because of electronic contribution to specific heat. Okay, whereas the second term, the T cube term, it's because of the phononic contribution to the specific heat. Phononic contribution to specific heat. So these are the two terms which contribute to the net specific heat at low temperature. So therefore option A is the correct one here. Let's take a look at the next problem. So we are given a system of 3 particles and we are supposed to distribute them in 4 non-degenerate energy levels. Okay, the possible number of ways of distribution when the particles are treated as distinguishable, and then the second case for identical boson. Okay, so here we are having a situation where we are having n is equal to 3 particles. Okay, 3 particles, and we are having 4 different energy levels. Okay, and these are non-degenerate energy levels. Okay, so now the question is, in the first case we have to treat the particles as distinguishable. So when the particles are distinguishable, so that means there is no there is going to be no occupation constraint on the number of particles that a particular level can have. Okay, so now let's try to take a look at the first particle. So the first particle, it's having 4 different options to be in any of the energy level. Okay, the first particle, it could be either in the in the first energy state, or it could be in the second, third, or fourth. So that means the first particle is having how many options? 4 options. So it could be in any of the energy state. Okay, similarly the second particle, it could be also in any of the energy state independent of the position of the first particle. So there are 4 options available with the second particle also. Similarly the third particle will have also the 4 option following the same argument as I just discussed. Okay, because there is no occupation constraint on the any of the energy level, because we are treating a system of distinguishable particle. So the distribution of the putting the next particle is completely independent from the position of the previous particle. So it's a completely independent process. Okay, so that means the total number of ways will be 4 into 4 into 4, that is equal to 4 power 3, and that is nothing but 64. So when we treat the particles as distinguishable, so we are having 64 different ways. Okay, now so in the second case, when we treat the particles as boson, it's the second case when we treat them as boson. Okay, so in that case we are having n is equal to 3 identical boson, and the correspondingly the number of energy states in which we are supposed to distribute, that is equal to 4. These are you can say the most equally probable energy states. Okay, so now for the bosonic system, the corresponding number of microstates, they are given by n plus g minus 1 factorial divided by n factorial into g minus 1 factorial. Now substitute the corresponding values of n and g here. So that is 3 plus 4 minus 1 factorial upon 3 factorial into 4 minus 1 factorial, and after solving it we will obtain that this quantity comes out to be equal to 27. So therefore the correct option is C here. Okay, when we are treating the particle as the distinguishable particle, so then we are having 64 possible ways of distribution, and when we are treating them as the bosonic particles, then we are having 20 different ways of distributions. Okay. So let's now continue with the next problem. The partition function of an ensemble at temperature T is given to us. Okay, so let's first write the partition function Z, that is equal to 2 cos hyperbolic E upon kt, where k is the Boltzmann constant. Okay, and then its power n. Okay, now the heat capacity of this ensemble at T is equal to Ey kV is given by x n kV. So we have to identify what is the value of x. Okay, so in order to determine the heat capacity from the partition function, so first of all we are supposed to determine the corresponding average energy of the system with the help of the partition function, and the relationship that connects the partition function with the average energy is given by the average energy E from the partition function, that is equal to minus curly beta of ln logarithmic of the partition function, and that is equal to, so that means we are supposed to take the logarithmic of the equation 1. So while taking the logarithmic, so n will come before the differential, so that means this is equal to minus n curly beta of ln 2 cos hyperbolic E upon kt. Okay, because it was power n, so n came before the differential. Okay, so now we have to differentiate this expression with beta, because this is in terms of beta, this is equal to ln 2 cos hyperbolic beta e. Okay, so after differentiating, what we obtain is this is minus n upon, I'm writing the result in terms of beta, and later on we will change it in terms of temperature. So minus n divided by 2 cos hyperbolic beta e, and then again its differential with respect to beta, so that means 2 sine hyperbolic beta e, and then multiply by e. Okay, so that is equal to minus ne, this is equal to minus ne, 2 will cancel with 2, ne tan hyperbolic beta e. Okay, let's call this as equation 2. Now the average energy is known to us. Now we can determine the heat capacity of the system, Cv. So now we need to change this in terms of temperature. Okay, Cv, that is equal to dE by dt. Okay, so that is equal to minus ne, so differential of tan hyperbolic E by kt, beta is 1 by kt basically, so that is secant hyperbolic square E upon kt, and then differential of E by kt with respect to t, so that will give us minus E upon kt square. Okay, so after rearranging these terms, so this is equal to we have been negative 2 times, so this will be n e square. So I am introducing okay, so what, instead of writing it like this, so this is equal to n k e square upon kt square, or e by kt whole square. So I have multiplied by k in the numerator as well as in the denominator, and then multiply by secant hyperbolic square E by kt. Okay, so let's call this as result 3. Now I'm going to change this in terms of tangent hyperbolic function, and then we will plug in the value of t is equal to E by kv, and then see what we will obtain. So Cv, that is equal to nk E upon kt square, and then secant hyperbolic square x, that is equal to 1 minus tan hyperbolic square x. So I'm replacing it with tangent 1 minus tan hyperbolic square E upon kt, and this can be rewritten as n nk E upon kt its square, and 1 minus then tan hyperbolic square, I'm going to write it in terms of sine hyperbolic divided by cos hyperbolic, and then rewriting it in terms of exponential, equivalent exponential functions. Okay, so this is equal to exponential e upon kt minus exponential minus e upon kt divided by exponential e upon kt plus e exponential minus e upon kt, its square. Okay, now because it's given that e by kv that is equal to t, it's given to us e by k that is equal to t. So now when we'll replace e by k that is equal to t, so we obtain nk 1 minus e power minus 1 upon e plus e power minus 1. So upon solving this expression, we will obtain this is equal to, so after solving this comes out to be equal to nk into 1 minus e square minus 1 upon e square plus 1. So after solving it, so plugging the value of e power 2 in this equation, so this comes out to be equal to nk into 1 minus 0.58. Okay, the value of this terms in the bracket, that's 1 minus 0.58. so the answer comes out to be equal to 0.42 nkb. That okay, so therefore the value of x is 0.42. Let's take a look at the next problem. The statement is two solid spheres A and B have same emissivity. The radius of A is 4 times the radius of B. Okay, so we are given that we are having two different spheres, and radius of the sphere A that is equal to 4 times radius of B. Okay, and then the temperature of A is twice the temperature of B, so that means temperature of A that is equal to twice of temperature of B. The ratio of the rate of heat radiated from A to that of B is, okay, so the rate of heat radiated, the rate of heat that is radiated from a sphere per second. So the rate, so that means we are talking about the power. So basically it's a power radiated by a sphere which is at certain temperature T. Okay, so that is given by power that's proportional to the emissivity of that sphere, its surface area, and then T power 4. Okay, so let's call this as equation 1. Okay, now because area it's proportional to radius square, so what I can do is I can write that it is proportional to emissivity, radius square, and T power 4. Okay, so by clubbing all the proportionality constant in one single constant. Okay, so that means from here what I can do is I can write the ratio of the energy radiated, or the power radiated by the sphere A to the power radiated by sphere B, that is equal to, because it's the both of the spheres, they are made from the same material, it's given that they are having same emissivity, so while taking a ratio the emissivity will disappear. So here the only dependence it's on the radius and the temperature, so Ra power 2 Ta power 4 divided by Rb power 2 Tb power 4. Okay, so Ra is given to be 4 times Rb, so 4 times Rb square divided by Rb square, and then multiply by Ta, which is 2 times Tb, 2 times Tb its power 4 divided by Tb power 4, so that Pa upon Pb, okay, Rb square will cancel with Rb square, and then we will have 16 factor of 16 here, and then TB power 4 will cancel with TB power 4, and then we will have another factor of 16. Okay, so that this is equal to 256. So therefore our answer is 256 here. Let's continue with the next problem. So an air conditioner maintains the room temperature at 27 degrees Celsius while the outside temperature is 47 degrees Celsius. So let's first draw the symmetric diagram here. Okay, so air conditioner basically it removes heat from the interior of the room. Okay, and then it rejects heat through the high temperature reservoir, which is the surrounding basically. Okay, so here it's given that T2 that is equal to 27 degrees Celsius. Okay, and that is equal to 300 Kelvin. Okay, now and while the outside temperature, so T1 is reservoir, that's the outside temperature, so T1 is equal to 47 degrees Celsius, and that is equal to 320 Kelvin. Okay, now the heat conducted through the wall of the room from the outside to the inside due to temperature difference is 7000 watt. Okay, so that means every second the heat that's coming from the outside into the interior of the room, okay, that is 7000 watt. So that means in order to maintain the temperature of the interior of the room at 27 degrees Celsius, we have to every second we have to pump out 7000 watt, or mean we have to withdraw the 7000 watt, that is equal to 7000 joule per second. So this much amount of heat we have to pump out of the room each second. Okay, so that means this quantity, this is equal to Q2 basically. Q2 is equal to 7000 joule per second. Okay, now the minimum work done by the compressor of the air conditioner per unit time is, so we have to evaluate what is the minimum amount of work done that is done by the compressor to remove Q2 amount of heat from this reservoir. Okay, so if we can immediately calculate W provided the heat rejected to the high temperature reservoir, that is Q1, it's known to us. Okay, and we can determine Q1 from the given information by with the help of a standard result that we obtain while talking about the Carnot cycle. Okay, so the work done is given by, so the work done that's required to extract 7000 joule per second from the room, that is equal to Q1 minus Q2. This is the standard result that we obtain while talking about the Carnot cycle. Okay, now for minimum work for minimum work the AC should run, the air conditioner should run or should follow the Carnot cycle, because that's reversible. Carnot cycle, that's reversible and most efficient. Okay, and therefore the result that we obtain in the while talking about the Carnot cycle, that is Q1 upon Q2, that is equal to T1 upon T2. This result we obtain while talking about the Carnot cycle in theory. Okay, so that means from here Q1 that is equal to T1 upon T2 multiplied by Q2. Okay, so T1, T2 and all these parameters, they are known to us. So that by substituting the value of these parameter, 320 divided by 300 multiplied by 7000, sorry. Okay, so that means Q1 is equal to, after doing the the calculation, this comes out to be equal to joule per second. Okay, so therefore W is given by Q1 minus Q2, that is equal to 7466.66 minus 7000, and that is equal to 466.66 joule per second. Okay, or that is equal to 466.67. You can approximate, because here again you will, after continuing the division, so we will obtain another factor of 6 here. So this is the answer. Now let's take a look at the next problem. The statement is A microcanonical ensemble consists of 12 atoms. So we are having a system of 12 atoms, n is equal to 12 here, with each taking either energy 0 state or energy E state. Okay, so out of these 12 atoms, either the atom could be in the 0 energy state or E energy state. Both states are non-degenerate. Okay, so it's given that G is equal to 1 for both of these states. Okay, if the total energy of this ensemble is 4E, it's given that total E total, that is equal to 4 times E. Its entropy will be, okay, so that means this is a constraint that this system must satisfy. So now we can notice that because we are having a system of 12 atoms, and we have to ensure that the total energy of this system is 4 times E, and that's only possible when we place 4 atoms here. They will give rise to a total energy of the system as 4E, and remaining 8 atoms they are here. Okay, so now the total number of microstates, that's omega, that is equal to the arrangements of the n is equal to 12 atoms, that is 12 factorial, and out of which 8 atoms they are placed in the ground state, and the remaining 12 minus 8, that is 4 factorial 4 atoms they are placed in the energy state E. Okay, so that is equal to 12 9 into 8 factorial divided by 8 factorial, and then 4 factorial, that is 4 3 into 2. So 8 will cancel with this, 4 3 are 12, and then that is equal to, no, I think I made a mistake there. Okay, here we will have a factor of 11 10 also. Okay, and then we will have 2 5 ja 10, and then this will give a factor of 495. That's the answer. So no, omega, this is omega. Okay, we haven't yet obtained the entropy. So the entropy can be obtained. Entropy, this is the omega, so entropy is given by the Boltzmann equation. So that is S is equal to Kb ln omega. So that is equal to Kb ln 495, and then evaluating the value of this ln 495, so this is equal to 6.2 Kb. So therefore here it is 6.2. That's our answer. So this completes the solution for this year.